All right, so it's the last lesson looking at graph algorithms, and as a complement to the previous one, in which we're looking at problems commonly referred to as the Chinese postman problem, where you want to begin and end at some point and visit every edge. This common type of problem is called the traveling salesman problem, in which it's similar, but you still want to begin and end at the same point, but instead of having to visit every edge, you just have to visit every vertice, which actually opens up a lot more options. In fact, while this formula is not something that you'll probably have to use much, in general, the number of possible circuits like this, or cycles, which is called a Hamiltonian cycle, one that begins and ends at the same vertex and visits every vertex once, is quite large. It's 1/2 n minus 1 factorial. And remember, factorial numbers, when you find the factorial of a number, you tend to get extremely large numbers. For example, if you have a graph with 9 vertices, and you calculate this, you'll find there's over 20,000 different possible paths. That's a lot. And so for these questions, quite often, it is deceivingly complex to try to find the perfect path, or to find the path that we know has the absolute shortest path, the shortest distance. So instead, quite often, we're just trying to find out what is a range of the shortest possible, an upper and a lower bound for the range of this minimum path, because it can get really quite complex quite quickly. And so there's a couple of algorithms here are called the nearest neighbor algorithm, which is how to find the upper bound for what would be the optimal route, and the deleted vertex algorithm, which is the way of finding the lower bound. And these, once we have this, if we've done it correctly, we can see this range, and perhaps ideally a fairly small range, to give us a sense of what that optimal part will be. Because again, actually finding the optimum path is quite often beyond the scope of what we're expected to do in this course, unless it turns out the upper bound and lower bound are exactly the same. Then we know what that optimal route would be. Or so I should say, we not know the route, we know the optimal distance, the shortest distance. And so let's do it. Let's use these two algorithms, this time with an adjacency table. Now we could draw this graph out, but everything we need is on this table. So this is a graph showing us, we call this as a cost adjacency table. So you can imagine this being the cost of traveling between different sites. All right, so I want to use the nearest neighbor algorithm, the one stated up here in blue, to determine what's the upper bound of the shortest possible route, which means the maximum possible value that we would have for the shortest route that visits all these vertices, all these sites, and back to the start. So if we're starting at A, if we had a graph, we would just look at point A and find the next vertex that's closest to it that we haven't already visited. In this case, if we look at the table, I look at column A and just find the smallest number, which is 5, which means I know I'm going to start by going from A to B, and I'll list these out. So A to B first, which has a distance of 5. From there, I'm now going to, it's very similar to what we did with one of the algorithms earlier. I'm going to cross this out so I don't have to worry about it anymore, and now look at column B. And as well, I'm going to cross out column A because we've already gone there. So this is what remains. So now I'm at B, and I can see I have a choice of several here. I'm going to go to point C, though. That's the shortest. So I'm going to go from B to C. As long as my screen doesn't slide away from me. That's a total of 6. So far I've gone 11 units. So I say what the units are, or its cost, so $11, I don't know. And then same idea. So I've gone from A to B, B to C. I'm now going to cross out this, and look at now row C. There's only a 7, 10, and 12, and so I keep going, finding the smallest one. So now I'm going from C to D, which is 7. Cross that out, and now look at D. The shortest one left is 9, so I'm going from D to E. I'm just about done. So now I'm at E, and the only option is to go to F, obviously, because that's all that's left. So I'll go to E to F. But I'm not done yet. And that's because now I'm at F once I add up the 6, but we still got to get back to the start. So lastly, I got to go back from F to A. And so the distance from F to A is 7. And so we got to remember, we always got to get back to the start. There we go. So now I add all this up, and we get 40. So we call that the upper bound, which means we know not what the optimal path here is. We don't know the optimal value of that path, but we know it can't be more than 40. It's less than or equal to 40. And now we want to do a different algorithm to find the lower bound. And then we can see the range of what this most optimal path might be. So for the lower bound, we call this the deleted vertex algorithm. First, we start by, appropriately enough, deleting a vertex. And quite often you're told which one to delete. So I'm going to erase all my messiness here. But it's telling us to delete vertex B. So for a moment, let's pretend vertex B is not there. So on a graph, you can erase it or scratch it out for a bit. On a table, I just cross it out. So for the time being, vertex B is not there. And then I now want to create a minimum spanning tree from what remains, which we've done in previous lessons. And so I'm not told where to start, so I'm going to look at any one of these rows. It doesn't really matter where I start. I'm going to be boring and start at A. And so if I'm starting at A, then with a table, we cross out row A, put a 1 above the A here, and look for the shortest value below, which is going to be 7. So I'm starting by going A to F. And then I cross out the F, put a 2 above column F, and look at either column F or column A and find the smallest value, which in this case is that 6 right here. So I'm then going from F to E. And ideally, you've already learned this from our previous lesson, so I can do this fairly quickly. Cross that out. Sorry, don't cross that out. Cross out the F down there, I already did. Cross out the E, and then put a 3, then look at columns A, E, and F, and find the shortest value there, which should be this 9. Yes, this 9 right here, E to D. Cross out D, put a 4 up here, look at any 4 of these. The smallest value here is now DC, the 7. And then once I cross out the C, notice there's nothing left. So at this point, I have created a minimum spanning tree involving all the vertices except B. Well, we got to stop ignoring B. So the last step for this deleted vertex algorithm is to now create a subgraph by adding back the 2 deleted edges with the lowest weight that still connect to the tree. So I now got to pay attention to B again. So let me just erase all this, if it lets me erase it. All right, so now, if I were to sketch this out, what I've drawn so far, I have a minimum spanning tree that ignores B. So now we want to bring B back into it. And so if I look at B, I need to find the 2 lengths that are the shortest that connect. And so in this case, that's going to be BA and BC. Those are the 2 shortest, and they both connect, because if I look right here, there's both an A and a C vertice being used. So I want to add BA, and I want to add BC back into it. So if you actually sketched out this minimum spanning tree, it may not be itself the right cycle, but what we know is that if we add up all these values, it will tell us what the lower bound is, which means the optimal root will be greater than or equal to this. And if we add all this up, we indeed get 40 again. So this is one of these rare times that we actually know exactly the length of the optimal root, or we know the cost, I think it says here, of the optimal root that connects every vertice, because the upper bound and lower bound are the same. So I know it must be 40. 40 must be the optimal path, cost, whatever you want to call it. Although quite often we'd have something where maybe the upper bound is maybe 42 and this is 38, and we know it's somewhere in between there. But in this case, if they're the exact same, then we actually know it. Just don't expect it to happen very often. That said, I want to do similar things here, but with an actual graph, which may make it easier, maybe it's more confusing. For this though, this is all one question, all relating back to this beginning, which shows the time in minutes to walk between 5 houses. As it says, some of the houses are not connected by direct paths. So first, let's state the quickest possible routes and their lengths between the following pairs of houses. So from B to E. So from B to E, the shortest possible length is actually going to be going here and here. So BDE. And that length is 5 plus 2, which makes 7. Okay, that's the shortest possible route there. I want the shortest possible route from B to C. Again, your eyes probably are drawn to that 15, which may be the shortest, just don't assume it is. And it is not actually. The shortest possible route from B to C is to go up here and down here, 10 plus 3. So BAC. And lastly, I want to go the shortest possible route from C and D, which again, definitely look at the 18 first, but is there anything shorter? And there most definitely is a lot shorter from here to here. It's 7 plus 2, so CED. All right, with that said, let me erase some of those there. Next, I want to complete the graph showing just the shortest distances. So a lot of this we've already done. For example, if I just look what I've already written, B to E is 7, so I'm going to draw that in here with a 7. B to C is 13, so I'm going to draw that on here, right here with a 13. And C to D is 9, so I'll draw that here with a 9. And just continue for all the rest. And if I look at all, compare back to the previous image and just make sure I don't just copy the numbers, I make sure I write down just for the shortest possible path. So between A and E, 8 is indeed the shortest. Between A and B, 3 is indeed the shortest. Between E and D, 2 is indeed the shortest. But for these diagonals, I haven't figured out these two yet. What are the shortest routes? And so from B to D, if you look at the combinations, the shortest route is going to be 5, just what's actually given to you. I also have, actually there's a few more I missed. I have from E to C, the shortest possible route there is going to be, just the 7 that's given to us. Is that everything? One left. There's the last one. So many lines. From A to C, which again is given to us as a 10, and that is indeed the shortest length. So let me double check, but I believe, A to D, that's the one I haven't done yet. A to D, the shortest way to get from A to D is to go like this, so the shortest route is 10. All right, so what I have here compared to the original image is not the exact same values. These show just the shortest paths. All right, so this is now actually much more helpful. And I believe I have every side labeled, every edge I should say labeled, yeah. All right, so now we have a student lives at C and wants to deliver invitations to her friends at the 4 other houses. How nice, starting and ending at her own house. So let's find the upper bound, let's find the lower bound for the shortest route we can take. So using the nearest neighbor algorithm, this is now what we did before, but more visual, starting at C. I look at all the edges adjacent to C and find the shortest one. And the shortest one is going to be C to E, which is 7. So I will write down C, E. That's it. This may not be the actual path, because again, this is just going to give us the upper bound. Then next, from any of the vertices, either C or E, I find, hold on. Yeah, the nearest. Look at any of them that haven't been visited yet. My apologies, I'm tired. I find the next shortest one is E to D, right here. So that's 2. And then the next shortest one that connects to those is D to B, which is right here. That's 5. The next shortest one that is connected is B to A, which is 3. And then we visited all the vertices. Now we need to go back home. And so the shortest way back is from here to here, which is 10. So keep in mind, I have come up with a circuit. I just can't be guaranteed it's actually the best. But I know this will give the upper bound. So I know that this is going to be close to the best, if not the best. If I add this all up, I get 27. These are all in minutes, so it's 27 minutes. Which tells us that no matter what, the most efficient route cannot be more than 27 minutes. But that may not be the most efficient route. Sorry, the most optimal route. So now I want to find the lower bound. And if it actually ends up being 27, then we know this is one possible optimal route. But for the deleted vertex, I'm going to just erase my highlighting, but keep the values. This time, to find a lower bound, I'm told to delete vertex C. So temporarily, I want to ignore vertex C, and these are not, just pretend it's not there for a bit. And so then what I do is I find find the lowest, make a minimum spanning tree, find the lowest length, which is going to be this 2 here. So I start there. So DE. And then find the next lowest, which is going to be DB. Oh, helps if I can write. Which is going to be DB is 5. And keep creating this minimum spanning tree. Next, it's going to be BA, which is 3. And now notice, because we deleted vertex C, we have created a minimum spanning tree that connects everything we have here. But the last step now is to realize, okay, poor C is still there, so I need to make 2 more connections, the shortest 2 connections that we have. And the shortest 2 connections from C to this tree are the 7 right here and the 9 right here. These are the 2 shortest. So I'm going to add those 2 in. So I put in, what were those? EC and DC. So an extra 7 plus 9. That said, notice what I just sketched is not actually a cycle, but the total number of, if I add this all up, will be the lower bound. So just keep in mind, please don't think that what I've created here is the optimal route, but it tells me the lower bound for the optimal route. And if you add all these up, we get 26 minutes. We call that the lower bound. Which means we are now certain that to get from C and end at C and reach all the homes, it's going to be most 27 minutes and minimum 26 minutes, which means we're pretty certain how long it's going to take.